Here is a combined summary of the 4 pages. This research paper investigates weighted linear hyperbolic cross-polynomial approximations of functions on road from weighted Sobolev spaces of mixed smoothness, WR, P, W, road, and their optimality in terms of Kolmogorov and linear n-widths. The approximation error is measured by the norm of the weighted Lebesgue space LQ, W, road, where the weight W is a tensor product Freud weight. The paper introduces the concept of weighted Sobolev spaces, characterized by a specific norm, and defines the norm of a function in WR, P, W, road, as the sum of the LP, W, road, norms of its weak partial derivatives. It also introduces the concept of linear approximation, where a central symmetric compact set F in a Banach space X is approximated by elements from a fixed finite-dimensional subspace L. The paper proves the asymptotic optimality of polynomial approximation by de Laval-Poussin sums of the orthonormal polynomial expansion of functions with respect to the weight W2 in terms of relevant linear n-widths lambda n and Kolmogorov n-widths dn for 1 is less than or equal to p. Q is less than or equal to infinity and d equals 1. For 1 is less than or equal to p, Q is less than or equal to infinity and d is greater than or equal to 2. The paper constructs linear methods of hyperbolic cross-polynomial approximation based on tensor products of successive differences of dyadic-scaled de Laval-Poussin sums, providing upper bounds for the error of these approximations. The paper focuses on the linear hyperbolic cross-polynomial approximation of functions with mixed smoothness on road, introducing the Kolmogorov NWIDTH and linear NWIDTH as measures of the optimal approximation error. It proves the right convergence rate of lambda n and dn for some particular weights w and d is greater than or equal to 2, and introduces a new linear polynomial approximation method V(n) based on the tensor product of successive differences of dyadic-scaled de Laval-Poussin sums. The results provide upper bounds of the high-dimensional linear n-widths and Kolmogorov n-widths, generalizing previous results on the approximation of functions with mixed smoothness. The paper investigates linear polynomial approximations of univariate functions from WRP, W, R, in the norm LQ, W, R, with a focus on de Laval-Poussin and Fourier sums of orthonormal polynomial expansions. The approximation error is measured in the LQ, W, R, norm, and upper bounds are established for 1 is less than or equal to p, Q is less than or equal to infinity. Asymptotic optimality is proven in terms of linear n-widths lambda n, WRP, W, R, LQ, W, R, and Kolmogorov n-widths dn, WRP, W, R, LQ, W, R, for 1 is less than or equal to Q is less than or equal to p less than infinity. In the multivariate setting, the paper constructs linear methods of hyperbolic cross-polynomial approximation and provides upper bounds for the error of these approximations for various pairs p. Q with 1 is less than or equal to p. Q is less than or equal to infinity. For specific weights W with lambda equals 2, 4, the paper proves the right convergence rate of n-widths lambda n, WR2, W, road, L2, W, road, and dn, WR2, W, road, L2, W, road. The paper defines the best approximation of a function f by polynomials of degree at most m, denoted as E_m, f, and presents several inequalities involving this best approximation. The properties of operators v_m and s_m are discussed, including Markov-Bernstein type and Nichols-Key type inequalities, which provide bounds on the derivatives and norms of polynomials. The authors define unidimensional operators v_m, k and s_m, k, used to represent functions as series, and prove absolute convergence in the L_q norm. Norm estimates for each term in the series are provided, leading to a theorem stating that the L_q norm of the difference between a function and its approximation by polynomials of degree n is bounded by n_r_lambda, p, q, where r_lambda, p, q is a positive constant. A corollary provides bounds on the approximation numbers of the identity operator between certain function spaces, demonstrating the effectiveness of the polynomial approximation method. The paper discusses the approximation of multivariate functions using weighted hyperbolic cross-linear polynomials, starting with a series representation for functions in the space LQ, W, R, with absolute convergence and norm estimates. A theorem provides upper bounds for the error of these approximations and linear n-widths, as well as Kolmogorov n-widths for various pairs of p and q with 1 is less than or equal to p, q is less than or equal to infinity. Orthonormal polynomials with respect to univariate Freud-type weights are introduced, and divariate polynomials are defined as the product of these univariate polynomials, with Parseval's identity established for these polynomials. A lemma states that if a function f has derivatives in Lp, W, ρ, up to a certain order, then its derivatives of lower order are also in Lp, W, R, E, for almost every z element of ρ minus E, which is used to construct approximation operators for functions in Lp, W, ρ, using the Smoleic algorithm. Unidimensional and d-dimensional operators v2k, vk, and ek are defined to approximate functions in Lp, W, ρ, with an upper bound established for the error of these approximations in terms of the norm of the original function in Wr, P, W, ρ. The right convergence rate of n-widths and Kolmogorov n-widths for certain weights and pairs of p and q is discussed, achieved by establishing connections between the approximation error and the norms of the original function and its derivatives. The analysis demonstrates the absolute convergence of a series in the space LQ, W, ρ, leveraging theorem 2.3 and lemma 3.1 to establish an inequality for the norm of the operator ek1f. This is further simplified to an inequality involving the norm of the function f in Wr, P, W, R2. Lemma 3.3 states that for every f element of Wr, P, W, ρ, the function f can be represented as an absolute convergent series in LQ, W, ρ, with an upper bound provided for the norm of the operator vkf. The operator vxi is introduced as a linear bounded operator in LQ, W, ρ, defined as the sum of vkf over k element of nd0 with k, 1 is less than or equal to xi, with its rank calculated to be approximately 2xxd-1. Theorem 3.5 establishes that for any function f in the Sobolev space Wr, P, W, ρ, and for xi greater than 1, the difference between f and its approximation v xi f can be bounded by the norm of f in the Sobolev space. This theorem provides a key insight into the approximation properties of the linear operator v xi, which is crucial for understanding the behavior of functions in the Sobolev space. Theorem 3.6 extends this idea to the context of NTERM approximation. It states that the nth approximation number lambda n can be bounded above by the supremum of the norms of the differences between f and its approximation v xi n, where xi n is the largest number such that the rank of v xi n is less than or equal to n. This theorem has significant implications for the study of approximation properties in Sobolev spaces, particularly in the context of numerical analysis and computational mathematics. The subsequent sections introduce the linear operator S-xi, which is defined as the tensor product of unidimensional operators. This operator is used to define a new polynomial subspace P1, xi, and to establish a connection between the approximation properties of S-xi and the rank of S-xi. Finally, theorem 3.8 is presented, which is similar to theorem 3.6 but applies to the linear operator S-xi instead of v-xi. This theorem provides further insights into the approximation properties of S-xi and its implications for the study of Sobolev spaces. In summary, these sections delve into the approximation properties of linear operators v-xi and S-xi in Sobolev spaces, providing crucial insights for numerical analysis and computational mathematics. The theorems presented establish upper bounds for approximation numbers, shedding light on the behavior of functions in these spaces and the efficacy of approximation techniques. The authors investigate the right convergence rate of lambda n and dn, where lambda n and dn are the n-widths of the weighted Sobolev space Wr2, W, ρ, embedded in L2, W, ρ. Specifically, they focus on the case where the generating weight W is given as in equation 1.1, with lambda equals 2, 4. The authors define the space our lambda W rho as the set of functions f element of L2 W rho represented by the series 3.1 with a finite norm. They construct a hyperbolic cross-polynomial approximation based on truncations of the orthonormal polynomial series 3.1. The truncation S** operator xi f is defined as the sum of f k pk over k element of g xi, where g xi is the set of k element of nd0 such that Rl r k is less than or equal to xi. The authors apply the Tikhomirov lemma to establish an upper bound for lambda n and dn. They construct a sequence xi n infinity n equals 2 such that g xi n is less than or equal to n and sup f element of our lambda w rho fs * operator xi n f L2 w rho much less than n minus r lambda log n r lambda d1. This yields the upper bound lambda n, our lambda w rho L2 w rho dn, our lambda w rho L2 w rho n minus r lambda log n r lambda d1. To prove the lower bound, the authors apply lemma 4.1 and construct a sequence xi n infinity n equals 2 such that g xi n is greater than or equal to n plus 1. They show that dn, our lambda w rho L2 w rho is greater than or equal to dn c xi n minus r lambda u xi n plus 1 L2 w rho equals c xi n minus r lambda n minus r lambda log n r lambda d1. Finally, the authors establish a norm equivalence between wr2 w rho and our lambda w rho for lambda equals 2, 4, which allows them to identify wr2 w rho with our lambda w rho in these cases. This leads to the main result, theorem 4.4, which states that lambda n wr2 w rho L2 w rho equals dn wr2 w rho L2 w rho n minus r lambda log n r lambda d1 for lambda equals 2, 4. The paper discusses the convergence rate of the right-hand side of equation 4.5, which is conjectured to hold true for every even r. This assertion is supported by the work presented in this paper, which explores the numerical weighted integration of functions with mixed smoothness. The authors draw upon previous research in this area, including the work of Dinh on numerical weighted integration and weighted sampling recovery of functions with mixed smoothness. The paper cites various references that provide a foundation for the research, including the work of Dinh and V.K. Nguyen on optimal numerical integration and approximation of functions on R equipped with Gaussian measure. The authors also reference the work of S. Jha and D. Lubinsky on necessary and sufficient conditions for mean convergence of orthogonal expansions for Freud weights. The paper's discussion of hyperbolic cross-approximation is informed by the work of Dinh, V. N. Temlyakov, and T. Ulrich, while the section on weighted polynomial approximation and numerical methods for integral equations draws upon the research of P. Jungens, G. Mastroianni, and I. Notarangelo. The authors also reference the classic work of A. Kolmogorov on the best approximation of functions and the survey of weighted polynomial approximation with exponential weights by D. S. Lubinsky. The paper's use of mathematical concepts, such as the theory of weighted polynomial approximation and the theory of best approximations, is grounded in the work of H. N. Masker and V. N. Temlyakov. The authors also draw upon the research of E. Novak and H. Wozniakowski on the tractability of multivariate problems and the work of V. N. Temlyakov on the approximation of periodic functions. The paper's conclusion is supported by the references cited, which provide a comprehensive foundation for the research presented. The authors' conjecture regarding the convergence rate of the right-hand side of equation 4.5 is a significant contribution to the field of numerical weighted integration and approximation of functions with mixed smoothness.